There is a floating city operating in the middle of the ocean right now. It has its own power plant, its own water supply, its own fuel network, and 5,000 people living and working inside it. That city is a U.S. aircraft carrier. And what keeps it alive is not just military strength, it is one of the most complex engineering systems ever placed on water. Here is exactly how it all works. Most people see the jets launching from the flight deck and assume the ship is just a very large runway. But underneath that deck, below the water line, hidden inside miles of pipes, cables, and pressure lines, there is a world most people never hear about. A world where every single day trained sailors fight a silent battle to keep power flowing, fuel moving, and water running. Without that battle, the jets do not fly, the ship does not move, the mission does not happen. What you are about to see will completely change how you look at these ships. Introduction. This video is going deep into that world. We are going to cover the nuclear reactors that power these ships, the aviation fuel system that feeds every jet on the flight deck, the remarkable process of refueling at sea, and the thousands of sailors whose entire job is making sure none of it ever stops. Before we get into it, if you find it remarkable that a warship this powerful can operate completely alone in the ocean for months at a time, drop the word "I love Navy" in the comments right now. Let us see how many proud Americans are watching today. Nuclear power, where it all begins. Let's start with the most important question. Where does all the power come from? A modern U.S. aircraft carrier like the USS Gerald R. Ford runs on nuclear energy. Not one reactor, two of them. The Ford-class carriers use two A-1B reactors that together produce around 700 megawatts of thermal energy. To put that number in perspective, that is enough heat to power a mid-sized American city. But raw heat is not what runs the ship. That heat boils water into steam. That steam spins massive turbines. Those turbines do two critical things. They turn the four propeller shafts that drive the ship, and they generate electricity. The Ford class produces around 104 megawatts of usable electrical power, roughly 3 times more than the older Nimitz-class ships. Now, why does it need that much? Because it is not just lighting hallways. It is powering the launch system that throws a 60,000-pound jet into the sky in 2 seconds. It is running 4 aircraft elevators, each one capable of lifting 130,000 pounds. It is running radar, weapon systems, communications gear, medical equipment, and the full daily lives of 5,000 people, all at the same time. Here is something most Americans do not know. The Ford-class reactors are engineered to run for approximately 25 years without new fuel. A carrier launched today may never need to stop for reactor refueling during its entire active service life. That is not just impressive engineering, it is a strategic advantage that no other navy on Earth can match. A ship that never needs to stop for fuel can hold its position in any ocean, for as long as the mission demands. The older Nimitz-class ships use A4W reactors, still remarkably powerful, producing around 64 megawatts of electricity. That is enough to power approximately 12,000 American homes. These ships require a full refueling and complex overhaul every 20 to 25 years. That overhaul costs around $4.5 billion and can take several years to complete. But when a Nimitz-class ship comes out of that process, it is essentially rebuilt from the inside, with upgraded systems and extended service life. The electrical grid. So the reactors produce the power. But how does that power reach every corner of a ship over 1,000 feet long? The answer is a ship-wide electrical grid that works like the power grid in a city, except this one floats and must survive combat damage. Power moves through high-voltage distribution buses at around 450 volts AC. These buses form redundant loops throughout the ship, so if one section is damaged or cut off, the rest of the grid keeps running. The Ford class also carries 4 gas turbine generators, each producing 26 megawatts that back up the system if any section needs additional support. On Ford-class carriers, this entire setup is called the integrated power system. Its key feature is that it separates propulsion power from ship's power, allowing the crew to redirect electricity exactly where it is needed at any given moment. During a launch cycle, massive amounts of power get routed directly to the launch system without disrupting anything else on the ship. That launch system is called EMALS, the Electromagnetic Aircraft Launch System. Every single launch requires around 100 megajoules of energy, delivered in approximately 2 to 3 seconds. That energy is stored in massive spinning drums below decks between launches, then released in one powerful surge when the pilot hits the catapult. The system can launch a new aircraft every 45 seconds at full operational pace. That is not just impressive, that is what air dominance looks like. Aviation fuel, JP5. Now let's talk about what keeps those jets in the air. Aircraft carriers carry a specific type of aviation fuel called JP5. It is not the same fuel used at a commercial airport. JP5 was specifically developed for naval operations because of one critical property, a flash point of 60 degrees Celsius. That means it is significantly harder to accidentally ignite than regular jet fuel. On a flight deck where fuel is constantly moving, jets are landing with hot engines, and ordnance is being handled nearby, that difference in flash point is not a technical footnote. It is a lifesaver. A Nimitz-class carrier holds up to 3.5 million gallons of JP5. The Ford-class carries approximately 2.5 million gallons. These are not storage tanks sitting somewhere visible on the ship. They are built into the lower hull below the waterline. As fuel is consumed, those tanks are filled with seawater to maintain the ship's balance and stability. Engineering and ballast management working together, one practical solution solving two problems at once. Getting that fuel from the bottom of the ship to the flight deck requires a network of stainless steel pipes running vertically and horizontally throughout the vessel. Pump rooms below decks are staffed by sailors holding the ABF rating, Aviation Boatswain's Mate, fuels. These crews operate high-pressure pumps pushing fuel at up to 900 gallons per minute per fueling station. On the flight deck, there are dozens of recessed connection points called fueling pits. A trained sailor can have a fighter aircraft connected and flowing fuel in under 30 seconds. During a full flight day, which can run 16 or more continuous hours, a carrier burns between 100,000 and 200,000 gallons of JP5. At that rate, even the largest fuel load lasts only a few weeks of sustained flight operations, which leads directly to one of the most impressive operations in all of military history. Refueling at sea, UNREP. Stopping at a port to refuel would make a carrier predictable, vulnerable, exposed. So the U.S. Navy built a different solution entirely. They bring the fuel to the carrier while both ships are moving in the open ocean. This is called UNREP, underway replenishment. Watching it in action is one of those moments that reminds you exactly what American military seamanship can accomplish. Here is how it works. A supply ship, typically one of the Navy's TAO-class oilers, pulls alongside the carrier. Both ships travel at matching speed between 12 and 16 knots. The gap between them just 150 to 200 feet. In the open ocean, with swells, with wind. A transfer rig is rigged between the two ships, and thick 7-inch fuel hoses are passed across. Fuel then flows at up to 400,000 gallons per hour. A full JP5 resupply can take 4 to 8 hours of continuous connected operations. During every minute of that time, both ships must hold their position precisely. One error in seamanship and those pressurized hoses could snap violently. The sailors who run UNREP systems train for months before they ever handle a live connection at sea. The supply ships used for these operations are the Henry J. Kaiser-class TAO oilers, each carrying approximately 180,000 barrels, around 7.5 million gallons of fuel. The Navy is now fielding a new class of supply ships, the John Lewis-class TAOX oilers. The lead ship, USNS John Lewis, was delivered in 2022 and has already completed multiple resupply operations with carrier strike groups across both the Pacific and the Mediterranean. Alongside the fuel, these supply ships also deliver food, spare parts, ammunition, and mail. Helicopters simultaneously fly cargo between the ships in a process called VRTREP, vertical replenishment, sometimes operating at the same time as the fuel hose connection. The combined efficiency of UNREP and VRTREP is what allows a full carrier strike group to remain at sea for 7 to 9 months without ever coming home. But here is what does not get discussed enough. All of that fuel, all of that power, all of that engineering, none of it functions without the people who run it, every hour of every day, in conditions that would push most. People to their limits. Freshwater, the quiet lifeline. Power and fuel capture most of the attention, but there is a third system running quietly beneath all of it, one that gets almost no coverage, yet is just as essential. Freshwater. A carrier cannot carry enough fresh water for 5,000 people across a full deployment, so it produces its own. Using a combination of reverse osmosis desalination plants and evaporators that run off waste heat from the reactor, a Nimitz-class carrier generates approximately 400,000 gallons of fresh water every single day. That water feeds the crew's showers, kitchens, laundry, and medical facilities. It also goes directly to the aircraft. Every jet that lands on a carrier arrives soaked in salt spray. If that salt is not washed off quickly, it begins corroding the airframe, the engine intakes, and the electronics. Every aircraft gets a freshwater washdown as part of its standard post-flight procedure. Without consistent daily freshwater production, the air wing would begin losing aircraft to corrosion within weeks. The freshwater system is not a comfort feature, it is a combat readiness requirement. The crew behind the systems. None of this runs itself. On a Nimitz-class carrier, the engineering department includes roughly 600 sailors managing non-nuclear machinery, electrical systems, and damage control. The reactor department adds approximately 300 more, all of them nuclear trained. Reactor operators go through one of the most demanding technical pipelines in the entire U.S. military. They attend the Naval Nuclear Power School in Goose Creek, South Carolina, a 6-month program covering nuclear physics, reactor theory, thermodynamics, and engineering at a college level. After that, they spend 6 additional months at a land-based prototype reactor, running real systems under direct supervision. Only after passing both phases are they qualified to step inside a reactor compartment on a deployed ship. These are 22-year-old Americans doing graduate-level technical work inside a steel hull somewhere in the middle of the ocean. The watch schedule never stops. Reactor spaces are manned 24 hours a day, 7 days a week for the entire deployment. Damage control teams are always staged and ready. Their response target is 2 minutes or less to any fire or flooding alarm anywhere aboard the ship. The ABF Fuels crew runs its own around-the-clock watch. During flight operations, they are moving hundreds of thousands of gallons of JP5 every hour, logging every valve position, every pressure reading, every connection. One contaminated fuel load could down a jet. One pressure failure during a fueling cycle could start a fire on a deck full of armed aircraft. These sailors receive almost no public recognition, but they are the reason the jets fly. Emergency systems and damage control. And when something goes wrong, because at sea things do go wrong, the ship is built to absorb it. Every carrier carries multiple layers of backup power. Emergency diesel generators can maintain critical systems if the reactor plant goes offline. The integrated power system on Ford-class ships can automatically reroute power around any damaged section of the grid without crew intervention. For fuel fires, the flight deck is equipped with AFFF systems, aqueous film-forming foam, capable of discharging at over 250 gallons per minute to smother an aviation fuel fire before it spreads. Every single sailor on a carrier, regardless of their job rating or department, receives firefighting and damage control training. This is not an elective, it is survival protocol. JP-5 tanks are positioned below the waterline and surrounded by structural protection. Each tank is isolated by individual valves, so a problem in one section does not automatically compromise the entire fuel supply. The ship can lose portions of its fuel system and continue operating. This philosophy has a name in the Navy: damage control. The idea that a warship must be able to take a hit, absorb it, and keep fighting. Every system has a backup. Every backup has a procedure. And every sailor knows that procedure by memory. The bigger picture. Step back for a moment and look at what all of this means together. A U.S. aircraft carrier can travel to any ocean on Earth without stopping for fuel. It generates its own electricity, produces its own water, carries its own aircraft, fuel, and crew. It can sustain full combat operations for weeks, be resupplied at sea without slowing down, and continue the mission indefinitely. No other nation operates anything like it. The U.S. Navy currently runs 11 nuclear-powered aircraft carriers, 11 self-sustaining floating cities, each capable of projecting more air power than the entire air forces of most countries combined. The cost to build the USS Gerald R. Ford was approximately $13.027 billion. That investment represents decades of research, engineering refinement, and the combined expertise of thousands of American designers, shipbuilders, and military planners. But what actually makes that investment work, what makes the ship go, is not any single reactor or fuel pump or launch system. It is the people who run all of it. The reactor operators who spend a full year in training before they touch a live shipboard reactor. The fuel sailors moving millions of gallons of JP-5 through steel pipes below a deck where jets are landing every 45 seconds. The electricians keeping 450-volt buses running through a hull that is constantly moving, vibrating, and occasionally hitting the full force of a North Atlantic storm. These sailors do not get the magazine covers. Their names are never attached to the aircraft flying above them. But without them, not a single jet ever leaves that deck. Conclusion. That is the complete picture of how an aircraft carrier manages fuel and power at sea. From 2 nuclear reactors generating over 100 megawatts of electricity to 3.5 million gallons of aviation fuel moving through steel pipes beneath the flight deck, to 400,000 gallons per hour transferring between ships in the open ocean, every piece of it is the result of generations of American engineering and military dedication. If this gave you a deeper respect for the men and women who serve aboard these ships, hit the like button and subscribe. These videos take real effort to produce, and your support is what keeps them coming.